This is me. Yeah, I'm a penetration tester for Portcullis. I've been there for about 14 months now. One of my specialities is messing around with binary protocols, messing around with network protocols, messing around with flat files, Windows reverse engineering, Windows internal stuff, Windows binary applications. So that's the kind of stuff that I really enjoy doing. So I'm going to talk to you today about some sort of generic techniques into breaking these binary protocols from the ground up. So yeah, these are all my contact details. And this is all the corporate information which I am required to tell you about. So read them if you want. Right. So yeah, there'll be a quick introduction. We'll go over some background information to the talk, some general analysis techniques for digging into these binary network protocols, identifying bad implementations of cryptography. So often you'll find that people who've implemented their own binary protocols will have also done silly things with the crypto. They won't have just TLS wrapped it with a decent implementation. They'll have gone and put their own things in there. And then we're going to put things together and come up with some conclusions. Basically, this entire talk is based around some issues that I found in a very popular piece of networking equipment. So how many of you saw the abstract and saw the little disclaimer at the bottom saying, oh, we're not quite sure what we're going to be talking about, whether we can tell you or not, and came here in the hopes of getting some 0 day? Well, this is going to be good. I'm particularly proud of some of these animated GIFs. So the subject of this today is a load balancer. Anybody know what that is? Somebody said it. It's a Citrix NetScaler. So in reality, it'll probably look more like that. So it's a little less shiny. These are the older style ones. I'm not quite sure which revision this is. But yeah, these things are essentially, well, I'll tell you what they are in a minute. So this is what it says on their website. That first lot is a load of way too much for me to read, but these second two quotes here are absolute gold. Like, marketing material is brilliant. Combines a comprehensive attack detection database to immediately identify and block known security threats, along with a positive security model that blocks 0 a day attacks. I'm sure that really works. Oh, by the way, does anyone here work for Citrix? Nobody? Well, when this goes out, if anybody from Citrix is watching, sorry. I know they've already spoken to me, but sorry. And yeah, of course, blocking 100% of attacks. Yeah, I'm sure. So there's the reality. It's 90% bullshit. So it's a load balancer, it's an SSL endpoint, it's a VPN endpoint, it's available as a physical device, which you've seen. You can get it as a virtualized appliance. It has the various Citrixy stuff, so you got ICA, which is the remote desktop style thing, XenApp and all their other various things, and standard security features, which is basically a firewall, but they've got some particular things that matter to it in terms of it being an SSL endpoint and things like that. So the history of this is essentially that the second week I started at Portcullis, Tim, the guy sat there, handed me this big black box and said, mess with that. So I said, okay, that'll be interesting. So I started digging around in it, spent a couple of weeks playing with it, found some very interesting things, started reverse engineering various bits of it, and worked out that there were quite a few things wrong with it. So I compiled all of this research into a paper, and we sent it off to Citrix about 7 months ago. And it's now been 7 months, and they've now patched 2 of the issues. We actually had a conference call with them yesterday at 4:30, finally going over, but we've essentially decided that it's been a long time, the contact level has not been brilliant, so therefore we've gone ahead and decided that we're going to disclose this stuff. However, that being said, Citrix have apologized for not being in contact with us quite as much as as we would have liked them to be, and they're going to go. We're working with them going forward to try and improve the security of their products as well as their sort of handling of further issues. So they're doing pretty well. So the initial approach to looking at the device. First thing, look at the physical ports, because I like playing with hardware. Hardware is fun. You can find all sorts of crazy shit in hardware. So the first thing I did was spin it around, take the cover off, have a look, see what I can find. Unfortunately, not a whole lot, but we'll go into that in a minute. Analysing the network footprint, so that's a posh way of saying nmap. Basically poking around, having a look at what it exposes on different ports, because obviously you're going to have, with it being an enterprise networking piece of equipment, you can have different ports that are set up for different things, so you can access management over these ports, and these are external, these are internal, blah, 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 blah. So yeah, probing the services for interesting things, so connecting to them, trying to work out what they are, what they do, whether they maybe say something really silly, and you go, oh, okay, why's that doing that? And then sniffing traffic using during normal operation, so digging while it's just actually doing its job, and then sniffing the traffic whilst it's doing administrative tasks. So for example, if you're logged into the admin panel, what's it doing there? So the physical ports, as I said, weren't actually that interesting. There's a serial port, so it's standard DB9 and Ethernet RJ45, so there's not a whole lot to look around in there. So the serial port, as I said, standard DB9 connector. We go through to that on a standard 9600 board connection, drops you to a management shell. You can manage the device, reset passwords, blah, blah, blah. Physical requirement, obviously, it's designed for if you walk into the DC, walk up, and you need to fix something on it, you can go in and directly configure it. But we did discover a special logon. There's a special logon that is kind of documented. You can find out about it on the Citrix forums, and some of the Citrix support guys do talk about it, but I don't believe it's in the main real sort of documentation that they publish. So it's kind of interesting, but you can't do a whole lot with it really. So then we start looking at the network level. So it's got TCP ports open, port 22 for SSH, 18443 for the configuration utility over HTTP or HTTPS. The user can go to either. 3008 for the, this is a Java applet within the configuration utility. So the configuration utility is basically just like a web page with a Java applet embedded in it, and it doesn't really do anything else. You use the Java applet to configure the whole thing. If you visit it over port 80, then the Java applet talks over port 3010 and does everything in the clear. If you visit it over HTTPS, then it talks over 3008 and does that wrapped in SSL. Port 4001 for Citrix ITAs, that's a standard port. 7776 runs an unknown service. If you connect to it, it just immediately kills your connection. I don't know what that's for. I never worked it out. 27,000 and 52334 is the FlexNet licensing stuff that they use on there. Not a whole lot interesting with that. So the main thing that we're going to be digging into is the stuff on 3008 and 3010. Now the console management, when you connect via SSH, you log in with a username and password as you normally would, but instead of, there's a default which is NSRoot. You can just log straight into that if they haven't changed it. It's not very smart to do. NSRecover is the alternative one that we were talking about a minute ago, so the unusual one. It seems to be that so that one doesn't appear in etc password. It seems to be like some sort of special account that's built into the SSHD. Not entirely sure how it all works. There's no obvious way to change the password for it, but on a few of the devices that we looked at, the passwords were changed, so it may well be that Citrix can change it, or there is some sort of documented way. I've just not found it. But when you log in, you don't get an SSH prompt. You don't get a standard, bash shell or whatever. What it actually drops you to is a menu-based configuration system. So what they've done is they've taken this SSHD and then basically piped this management utility into it, so that when you log in, you just drop into that. So that there's no real sort of like breakout from that. well, there is, but essentially you do this menu-based configuration. So they have a set of, it's a little bit like using, I don't know if you've used diskpart or something like that. So you type diskpart and then you go into certain submenus and you can go back and the usual kind of thing. But if you have admin rights, you just type shell and it drops you to a shell prompt as root, which is quite nice. Now, reversing the Java applet. How many of you here have reversed a Java applet? Or at least had a look or a try. Right, so I found them you. Basically, Java is a just-in-time compiled language. It's quite similar to .NET. So if you compile the application, because it's such a reflective language, it's actually relatively trivial to get the almost original source code back, bar comments. Like everything basically gets compiled in because it's essentially a machine-readable description of the code that you've put in there. So you can reverse engineer that quite easily. There's lots of tools to do it. I use JD GUI. It's quite a nice tool. You literally just drop the executable in there or the jar in there, and it literally just tells you all of the source. And you just go through and read it all. It's like being back in an IDE, and you can export it all out as text, so you can grep through it or whatever. And as I said, you can use grep to find interesting things, certain things that you might discover quite easily with grep. Some things are a bit more contextual. And the documentation gives you a bit of context as to which bits of code are important and which bits aren't and what they might be doing. So you might grep for something and then go, I have no idea what that's doing. And then you start to trace it back and then look through the documentation, and that gives you a better idea. Now, spot the fail number 1. Who here actually knows Java? Who here can tell me what's wrong with that or why that's stupid? If you can read it. I know you know, Tim. Yeah, so basically the validation of the certificate is just return true. So I hand you a certificate, and instead of validating it, you just go, okay, and just accept it blindly. So I could hand you an expired code signing certificate for the wrong IP address. Everything can be wrong with it, and it will just go, yeah, that's fine. As long as you give it a certificate, as long as it's well formed. So that's kind of bad. So that's in their code. So yeah, the problem with that obviously being that you can use that to man in the middle the connection. Next one. Same thing, .NET. So this is originally from their documentation. So they have an API that you can talk to, and they recommend using that. Not very bright. However, it also turns out if you Google a little bit of that code, like it turns out it doesn't appear very often that people write that. So if you Google a bit of it, some other people have put out open source stuff. Well, I say open source stuff, reverse engineered stuff from other Citrix products, and that's in another Citrix product somewhere. It's interesting. Well, it's still related to the next, but yeah. So, issue number 1. I told you I was proud of the animated GIFs. So there's no certificate validation on the SSL communications with the applet. So that SSL is when you go over port 3008, when you've gone to the website over HTTPS, the Java applet loads up and then talks back over port 3008 with the TLS wrapping. But if you can man in the middle that connection back, it didn't matter that they went over HTTPS. Their browser, it means nothing. You can just go through and pop those communications and see what's going on between the user's Java applet and the device itself. So, who here knows what Diffie-Hellman is? Right, so Diffie-Hellman, key exchange protocol. It's a bit of interesting cryptography. Essentially, it's a way for two parties to securely exchange a secret without an observer being able to work out what that secret is. So there's two types of Diffie-Hellman, ADH and DH. ADH is anonymous, so I know nothing about you, you know nothing about me, there's no prior authentication. And the problem with that is, if you man in the middle that, I might end up talking to somebody else. So I might end up going, okay, I'm going to exchange this with you, but actually I'm exchanging it with somebody else, and they do another exchange with them, and then they man in the middle and get in between. Diffie-Hellman normally uses an authenticated version of that, which essentially the initial handshake stuff that goes across is authenticated with with some sort of prior exchanged or agreed upon authenticity information. So when you normally do it, you might sign it with a long-term public key, long-term private key, and then somebody else can validate it with that public key. Now, the implementation that they use, in order to generate the random prime, they use java.util.random. Now, java.util.random is just a PRNG. It's like libc random. There's no guarantee of it being cryptographically secure. In fact, I can tell you flat out, it is not cryptographically secure. Don't use it for that. So there's a 32-bit seed on older systems. On newer ones, it's 48-bit, which kind of makes it hard to brute force the seed because the random generation isn't like a trivial bit of computation. It's a little bit more difficult to brute force, but it's still possible. But the problem is that because it's a PRNG, it's not a cryptographically secure random number generator. It's a pseudo-random function. It's not designed to be cryptographically secure. If you take a bunch of outputs from this, there are what's called predictor algorithms that people have written, which will tell you what the seed is based on like 5 outputs from the random number generator. So it's really bad to use that kind of thing for cryptography. And the seed is also based on a timestamp, so that really narrows down your values, because if you know that the applet started up roughly when you just saw somebody download a big bit of HTTPS data off of the Netscaler, you can kind of guess roughly the timestamp is going to be within this range, and therefore you've just cut the number of seeds down massively. So then all you need to do is guess that, have enough guesses, have enough outputs, be able to roughly work out what potential seed values there could be until you get them within this window, and then suddenly you know what the seed is, and then you can work out every random number that it will generate, and therefore you can work out what the Diffie-Hellman private information was, and then you get the secret, which means you win. So, sorry, there's a lot of maths in this particular bit. I'll say a lot. So the way Diffie-Hellman works is that you have a prime P and a base G. These values are sort of picked beforehand, and then in the way that it was implemented in their code is as follows. You pick prime P, base G, then you pseudo-randomly select a candidate secret value, so A apostrophe, which is the candidate secret value, i.e. I think I'm going to use this one, I need to check that it's all right first. Such that it's less than the max. So imagine I pick the number 3 as my P value. Now, 3 in terms of the number of bits you need to store the number 3, you need what? 2 bits, 3 bits? So my brain is not working today. A number of bits. Now, given that candidate number P, basically using the same sort of idea, how many bits do I need to store this number? So that's the maximum value that this will be. So basically what it does is it loops through and goes, okay, I need to pick another number that's smaller than this one. So if I pick a number such that it's got that number of bits, there's a good chance that I'm going to be somewhere around the right maximum value. So then it next checks that it's actually less than that value, and if that condition doesn't match, it loops around again, tries to pick another number. So what it's essentially doing is saying, okay, pick a random number. Does that random number satisfy these things? If it does, hooray, let's use that. If it doesn't, pick another one. Now, this is kind of interesting because the upper bound for that value is something that you know, because it's a public piece of information. So if I hand out this public piece of information and say to you, okay, I'm going to pick a random number, but I don't know whether it's going to satisfy these conditions, I'm going to loop around until I do it. Well, what happens if you work out how long it took me to do that? Based on that piece of information you know, you can start to work out how many iterations I might have done in order to hit that value. So by knowing this public value and knowing how long it took me to generate the private value part, you might be able to start working out some more information about how about what that value might be, or more importantly, about which values I discarded. Now, if you know that I discarded a whole bunch of values, you can know that those values have a certain property, like, for example, that they were too big. So if I say, okay, here's the number 1000, I'm going to pick a bunch of random numbers until I find one that's less than 1000. So if you know that it probably took me about 20 iterations before that happened, you know I had 20 numbers that were bigger than 1000 coming out of my random number generator, which means that you start to build this sort of model of, okay, well, he had about this many values. We know that, therefore, we might be able to build a predictor for that random number generator such that I can tell it, okay, I picked 60 random values that were larger than this. Find me a sequence. Find me a seed whereby this sequence is likely to have occurred. And then when we start to tie all this information together, we can start to look at, for example, well, if the p-value is quite high and has like a lot of its early bits set to 1, you know that all of the discarded ones must have also had those bits set to 1, because in order for it to be larger, it must also therefore have those bits set to 1. So you can start to work out these little things and start to unravel information about the discarded values and then start to work out this information about what the random number generator outputted. Now, there's also a function called munge in there, which made me laugh because it's a completely ridiculous name for a function. So they have this function called munge, and literally what it does is it takes an input value of some bytes and repeatedly XORs these fixed values, these static keys, over that information and then outputs them again. So it's like a really crap encryption algorithm. And it turns out that these byte values are these strings here. Now, the first one they look like landmarks in India. I don't know whether anybody recognizes those. I don't know what they are. And the bottom one is a company that used to make hard drive controllers. So I'm not really quite sure what that's all about. But anyway, yeah, so we've got 2 issues there. Issue number 1 is the weird Diffie-Hellman stuff, badly implemented. And issue number 2 is these static crypto things. We'll go into what they were used for in a bit. So, as I say, we have issues. Incidentally, that is my favourite GIF ever. This is so weird. So you remember how I said to anybody from Citrix who's watching, sorry? Things like this that... Right, I'm lazy, like really lazy. I really can't be asked to do this. So like breaking DH is hard, breaking RNGs is hard, it hurts my head, I have to do maths. My beard isn't big enough to talk about probability theorem. So yeah, I'm lazy, let's break it easier, in an easier way. So the binary protocol, digging around in that, and you'll see why that other stuff is relevant in a minute. Analyzing the traffic on port 3010, which is the plain text stuff. It's easy to look at. However, there's a clear text header, which has a bunch of stuff in there that I look at and go, okay, yeah, that looks like clear text to me, followed by something that's quite high entropy. So that looks either compressed or encrypted, or both. So a bit of guessing. So as I started to look at the protocol, look at how things changed, you can sort of see values that look like encoded integers. So like, for example, if you get 1 0 0 0 0 0 0 0, so you've got 4 bytes there, you kind of think, well, okay, well, that looks like an integer whose value is 16, because 1 0 in hex is 16, and then you've got a bunch of zeros after there, it looks like a 4-byte int. So you can kind of guess certain things. So then you go, okay, well, what does that number represent? Well, what about the length of the packet? So you work out how long the packet, the data blob was, and go, oh, look, that matches up. And then you get another packet, and you look at the 2, and they both match up, and then you've worked out that that's the length field. So then you look at other things like values that stay static, like, for example, the second field in there, which is a magic number. It's just 0x A5A5, which is just designed to identify this is actually the traffic you're looking for. A reserved value, which is just 0, because it was always 0, so I'm just going to guess that it's probably reserved. some kind of packet type or code. So what I was saying was a lot of, when you log in, you see a lot of different types, and then periodically you just see this value stay the same for certain ones, and then you start doing management tasks, and then more packets come through with different values in this field, and that kind of says to me, well, it's probably like some kind of command code. So, as a guess. Then some kind of flag, it kept like, it didn't really correlate to being a different type of function. It seemed to have different, it just seemed to be set slightly differently in different ones of the same type, the same like packet type, the same function. It's kind of guesswork. You have to try and build up this sort of pattern in your mind of what's going on by looking at all the different types of traffic that's going through there. And keep in mind, yes, I could have gone through and looked through the Java source code. At the time, I hadn't actually found the bit where they define the packets. It's quite a big source tree, so I was still digging around for that. So in the meantime, I did that. Then an unknown 16-bit integer and an unknown 32-bit integer, couldn't work out what they were. So the payload data is the stuff that came after this. So that was the clear text header. Now the payload data after that is all encrypted and stuff. So you can see there, this is one of these packets that kept repeatedly being sent. Now, I thought probably a heartbeat packet to say, hi, I'm still here, I'm still connected, don't drop my session. The same repeated pattern, but if you start a new session, that pattern completely changes. You get the same sort of repeating pattern, but you get different values. But for the same session, every packet, same values. And the first bit would sort of change a little bit, but then the rest would be all right, it would be all the same. So that, to me, is evidence of a repeated XOR cipher. I'll say that in the loosest terms. So essentially, they're looping some value, repeatedly XORing it over it. And as you can see at the bottom, you've got this looped string. I don't think you can quite tell, but it's like 8C, DC, 29, 8C, DC, 29, and it just carries on repeatedly. But the first bits are kind of have a little bit of that, and then a little bit that's changed, so it's like, okay, so what's being sent over there? Now, I just want to talk quickly about some crypto classification. Now, if I throw you a binary protocol that's got a bunch of data, and you want to work out, okay, well, what kind of crypto is being used over this data? You want to, without looking through the source code, let's say you don't even have the source code, let's say you can't even look on the device, it's some web app somewhere and it's just a black box. And you want to work out what exactly are they doing in terms of the crypto? Are they doing something smart? Are they using something custom? Are they using a block cipher? Are they using a stream cipher? Are they using something that is considered good, like AES, but implemented badly? Like, have they set it up badly? So the first thing you want to look for is patterns. If you see patterns, you know they're doing something wrong. Because proper encrypted data, you should never see patterns. It should all just look like purely random gibberish. So if you start to see these sort of repeated blocks of data, or like repeated little sequences of bytes, you can start to work out that maybe they're doing something a little bit wrong. Now, one of these other things is, if you maybe change a value slightly in your plain text input. So you can control the input and it gives you this encrypted output. So it's what's called, it's a form of differential cryptanalysis, because you're essentially taking what's coming in and comparing it with what's coming out and working out what those changes are. So essentially, you want to make a small change in your input and see how that changes the output. Now, if you just see that this tiny little linear change in your input just makes this tiny little change in the output, then you know that they're doing something kind of unusual. Either it's a stream cipher, or it's something like repeated XOR, because if you change one bit and one bit changes on the output, you know that they're doing something linear that's going across, for example, an exclusive OR operation. So if you've got a single byte input change, gives you a single byte output change, you've either got a stream cipher or something crap like repeated XOR. But then if you cycle to a new session and then try and do the same and you see different values, it might either be that they've changed the key. Yeah, they've probably changed the key, but if they don't, then you know it's probably a static key, which is interesting. Or if you know it's the same key somehow, I don't know, then they might be using something like an initialization value initialization vector, which then will also change the output of the value. So if you see that a single input byte changes a whole block of output, so like maybe 16 bytes or something, or 8 bytes, you know that they're probably using a block cipher. So the way a block cipher works is, given a block of input, a fixed length size of input, it's not only does it alter the values, but it also permutes the information around. There's two concepts, one's called confusion, the other one's called diffusion. Confusion is about taking a value and making it a different value. Diffusion is about taking that value and moving it around in the block. So, or splitting it out into its individual bits and then flipping those all around and then messing with them more and more and more. So by mixing confusion and diffusion, you get a half-decent block cipher. So it's, I think Claude Shannon is the one who came up with that terminology, I think. He's a smart guy. So yeah, if you see this chunk of output changing, then it's probably a block cipher. But if you do see that, it's a block cipher, but you know they've done it wrong. Because if they did it right, they would be using a block cipher mode that causes all of that other information to change once you change one bit. Changes in a block should always always sort of cascade across to the rest of the blocks and change the information more. So electronic codebook mode, ECB, is the most basic block cipher mode, which is essentially take every individual block of data, using the key, encrypt each one separately, using the transform, the crypto transform, which is like, for example, AES or Serpent or something like that, DES. You go through and encrypt each block separately, but you don't cascade them together, you just leave them all separately. Now, there's a great image of this, which you may have seen if you've ever looked on the Wikipedia page for block cipher modes. If you encrypt a bitmap image with AES, 256-bit AES, in ECB mode, and then you look at the output, like you put the bitmap header back on so it can actually be rendered, and you load it up, you can still tell it's that picture. You can still tell, like this, they use Tux, the Linux Penguin, as an example. You can actually see that image. You can still tell what it is. The colors are all messed up, but the reason that is because the same bytes of input for a block will always produce the same bytes of output for a block if you use the same key. So if you've got consecutive blocks that have the same plaintext, you'll get the same ciphertext, which means you know something about that plaintext, which is a bad idea. So because these pictures have the same sort of color information for a block, so if you've got a big chunk of white, you can actually see that all of these are the same. And then when you get a line, you get this transition where they're all different and it all kind of looks a bit messy, and then it goes back to being same patterns over and over again. So the patterns of data between blocks don't change in ECB mode. There's a way around that, and it's using a different mode. For example, cipher block chaining CBC, which is a much better way of doing it. So you know it's CBC mode if you change it and then only one block changes. You know it's ECB mode if you change it, that block changes, and all of the blocks after it change, but the ones before don't. So if you can put something like a big string of A's, and then you flip one to a B, and you see that everything after that gets changed, you know it's probably something like ECB mode where you get this cascading effect. So that's what I mean there by single byte input change is a current chunk plus all subsequent chunks. All the blocks after that change because you get this propagating thing. That still means they did it wrong because it still should just all be completely random. So yeah, if you put in a single byte change and everything changes, that probably means they're doing something right. Because what that means is they're using an initialization vector in there, which is the idea is that for every message, you choose this unique value, this unique IV, which then causes everything after that to become permuted completely randomly. You can't work out what's going on in there. So as I said with the CBC mode, it chains these together. The way it does that is for every plaintext block, it XORs it with the previous ciphertext block. For the first one, because there isn't a previous one, you use the IV, which then causes that to cascade across. So essentially what's happening is it's a little bit like a nonce value. It's a little bit like a salt. As long as it's unique, everything will always appear to be random. So if they do that right, you'll never know what's going on. You won't be able to work out whether it's a stream cipher, block cipher, what, because it'll all just look like gibberish. But if you can see these changes, these behaviors of the cryptography, when you change small amounts of information, you can start to get a picture of what's happening in that implementation. So you can start to work out that maybe they're using ECB mode, maybe they're using CBC, but they've got a static IV, so it's not changing. So that you get that cascade effect where you change one thing, everything after changes, but the values before stay the same. So the whole kind of idea behind it is you treat it as a black box, start sending it information, map how it changes as you change things, and you start to work out what's going on. And the final thing there is the block size of the chunk. So if you flip one bit and a whole block changes, by working out how much of that data, how much data changed, you can see the block size, which means you can narrow that down to, okay, well, how many block ciphers do I know that have a 64-bit block size or a 128-bit block size? So then you can start to work out maybe they're using AES, maybe they're using Blowfish, maybe they're using DES. You can start to work out what's going on. Now, decrypting the actual payload. So as I said before, it looked like repeated XOR. So I just took those bytes at the bottom and guessed that maybe they were like null bytes. So if they were null bytes and then you XOR them with a key, the result would just be the key. So they would be just transmitting the key inside the packet in the clear. You could just see it. So when I did it and XORed everything with it, get a bunch of zeros and then get stuff that looks like an actual proper packet header. And that to me went, oh, okay, yeah, they're definitely doing repeated XOR. So I eventually found the packet structure in the code, had a look around, did some more intuitive analysis to guess the fields, worked out what was going on. And this is what it said in the actual packet structure. So packet length, magic number, reserved, command, flag, error code, and dev number. So you remember I said there was a 16-bit and a 32-bit integer that I didn't know? It's those two at the end. Now this is a login packet. And the username and password looked encrypted. I couldn't work out what was going on. Now, remember I said that there was two functions called munge and those two static crypto keys inside there. Well, it turns out that if you XOR the username with the first one, and you XOR the password with the other one, you get the clear text username and password. So you can actually go through and decrypt all that information. So the high-level overview here, oh yeah, and close enough. I got pretty close to working it out without looking at the source, so I'm happy about that. So high-level overview. So the handshake packets at the start use DH to exchange a key for the session. That key is then used to encrypt the subsequent packets, so it's using this repeated XOR so-called cipher. And then the login packet is sent, contains the username and password obscured with that munging function. And the username and password, whilst they are ASCII, they're quite clearly, obviously there, they're not the ones that we entered, which is a little bit weird. And it turns out that we can do some interesting things with that. Basically, it comes out as a bunch of hexadecimal in ASCII, and it looks kind of odd. So the impact here is, if the user views it over HTTP, we can use the traffic on port 3010, which is in the clear, but encrypted with their custom algorithm. We can pop that crypto off quite easily just by watching for a single ping packet, which then actually contains the damn keys inside the packet because it's XOR with 0, which gives you that value. Then you can decrypt everything, decrypt all of the traffic all the way back, and you get the username and password. If they do it on 3008, so if they visited the applet and gone on via HTTPS, it goes, all right, best use port 3008, best be secure. And then they go through and just let any SSL certificate through. So you can just man in the middle of that, pop the crypto off again, you win. But what are those logins, the weird ones that we couldn't actually quite, that they didn't look right? Well, they're not your everyday login. So the accounts on the wire are like session IDs. So the username, so-called username, is 2 hashes, a bunch of hex, and then a null byte. And the passwords are just a bunch of hex again. Now, if you log into those, you log those in to the normal SSH. So basically, you log in over the panel, and you've sat there and sniffed somebody's connection, and you've decrypted that traffic. You then take those bits of information and use them to log into the NetScaler over SSH. and it drops you straight in. So you just stole somebody's session, and if the person that you were monitoring, the person whose traffic you were stealing, was a super user, you type shell, you get root. So that's your money shot right there. You win by sniffing the traffic or by man-in-the-middling them. Any questions? And more animated GIFs. Yes?
Just to clear up, you said this is obviously occurring when they're logging in over the Open Java ports. So it's only the Citrix Java client vulnerable is the default desktop client secure against this, and the
right,
HTML5
I don't know
client
about
secure
any of the other
against
clients. The Java one was the only one I looked at. It may well be that the other clients are vulnerable. It may well be that they're not. I would imagine the HTML5 one probably wasn't, because it's probably just doing like AJAX calls back into it. I would imagine that's in one of the newer NetScalers, because they have got some slightly different admin panel stuff on there. But the Java stuff, yeah, definitely vulnerable. Well, was vulnerable. They have now released a patch which fixes the SSL validation and apparently fixes the Diffie-Hellman stuff. We haven't reviewed this yet. They've said that they've released it, and they said that there's a patch out. We haven't actually had time to go back and look at it, because we only had the conf call with them at 4:30 yesterday to verify all of this. So, yeah. Anyone else? Yeah.
What kind of tools do you use to do the analysis and capture the data and replay and things?
So mainly just Wireshark, and then in order to like mess with the data again, I just wrote some custom stuff just to open up TCP sockets and start sending data to them. There are tools that you can use to do like binary, like on the wire manipulation. I've not found a good one yet. The one that I would use if I had to, I've forgotten the name of it now. Echo Mirage is a Windows one. So basically, it binds to the packet functions and lets you mess with stuff as they're coming in and out. There are a couple of ones that do that. But Echo Mirage can also detect if you're using standard SSL wrappers and then give you the stuff before the SSL, which is quite nice. I like that feature. It doesn't work with everything, but it works with like the Windows standard API for doing SSL. It works for, I think, a couple of standard like open source libraries as well. It detects those and goes, okay, I'm going to hook before that, rather than hooking the packet send function, which is quite nice.
The XOR encryption, where did you find the key for that?
So the XOR encryption is inside the, the ping packets that we're getting sent, because of the way XOR works, if you XOR a value with 0, you just get that value. So because the ping packets that were being sent had encrypted payloads, and those payloads were always 0, it just meant that they were sending the key in the packet, because you could literally just see it. Essentially, if it was still a static value and it wasn't 0, it still wouldn't matter, because you just XOR it with whatever static value you've got in the packet. If you know the data is there, you just XOR it back against, so you get the ciphertext, XOR it with the plain text, and that just gives you the key. So you can just recover the key through doing that. And then by getting that key, you can go back and decrypt everything else. Anyone else?
So, thanks very much.
Hang on, one last little bit. Sorry. So just quick special thanks. First off to Tim for just throwing this at me and putting me in the deep end my second week into the job. And also to Aaron Dowdeswell. He's the guy who handles our vendor disclosure stuff. He's done a lot of hard work over the Citrix stuff, keeping in touch with them, managing that. He's done a brilliant job. And obviously the BSides organisers for making this possible. And everybody who voted for my talk. Because you're awesome.